Hello, so welcome back to CV282. Today I'm going to talk about laminar and turbulent flow. So, in this topic, we are in the flow in closed country. I have many examples. So let's start with example number one. Determine whether the flow is turbulent or laminar if the glycerine, which is the type of liquid, is at 25 degrees Celsius, which is the temperature, um, flows at flows in a circular passage with a fabricated chemical processing device. So the only information that we need is um, there are like the numbers, value, and specification of the pipe and the water. And the diameter of the passage is 150 millimeters, and the average velocity of flow is 3.6 meter per second. So now, what we need here, there's like some hint. Actually, this is like I typed the hint, which is like an extra hint because in the original exercise there's no hint like this. In the lesson, if NR is like the Reynolds number, like N is like number, so like Reynolds number is, if it's less than 2,000, it means that the flow is laminar. If it's more than 4,000, it's turbulent. But what if it's like in between? Like it's normally you can see that if something is from, for example, NR is less than 2,000 and NR is more than 2,000 or like more than or equal. But in this case, like it jumps from 2,000 to 4,000, like it jumps completely. So in case that it's in between, it is impossible to predict, or it is in the critical region. So I guess this one is like something less than or equal, but in some case like there's nothing exactly to 2,000 or exactly 4,000, so you don't have to worry about that. So now um let's start in solving this problem. So for the Reynolds number, we can say NR is let me enlarge this one a little bit. So, or you can just write R or NR, it's okay, or NR like this, it's okay, it's fine. So I'll use this one, which is as the original part in the exercise. So NR is V, which is the velocity, D, E here, OA, um, this is like this. This is a symbol of it. So there are so many formulas of Reynolds number, but in some case like you need to like there are many formulas, but as you can see that the given number are D here, V velocity here. So and temperature here is like for you to reference to look at there's like another table that you have to look like it will be given in the exam. There will be types of liquid here, and it's constant, so you can just look from this one and at some specific temperature. So in this case, um for velocity here, it is 3.6 meter per second. D here is 150 millimeter, which is equal to 150 times 10 to the minus 3. So it's like 1,000 times smaller when we convert to meter. So now we get 1.15 meter. And then we have the density, which is the density of the glycerine, 1258 kilogram per meter cube. And then we have this number that is also from the table as well, So, well, when you see the table, you can just read it from the table and substitute the number here. So now we get all the necessary information. We can substitute here in this one. So now we have nr equals to velocity 3.6 meter per second multiplied by 0.15 meters multiplied by 258 and this will be kilograms per meter cube, and overall thing here is over 9.6 times 10 to the minus 1 Pascal per second. So now we have the final value, that is 708. So this 708 is the Reynolds number, and you can see that this one is less than 2000, which means less than 2000 is the laminar flow. So we can conclude that this is the laminar flow. So all the terms was expressed in SI units. There will be some times that we have to use the US units, like inch, feet, like gallons instead of liter, cubic feet per second instead of all this SI units. So now we can go to another exercise. There's no hint here, but we can look at the hint above because it is a similar type of exercise. So now we will use the same formula actually, but in case we can convert the formula into something else. So now let's read the problem together. Determine whether the flow is laminar or turbulent, the same. So we have to consider the n and r is whether less than 2000 or more than 4000 or in between. Okay, so if the water is 70 Celsius, even though we don't use a 70 or the temperature inside the formula, but we need to use it to look at the table. So flows in the hydraulic copper tube to this one, 32 millimeters multiplied by 2 millimeters wall. So the flow rate is 285 liter per minute. So now let's use the same formula here. It's nr equals to velocity, diameter over n. But in this case, we can substitute this one and get the V here. V here is like the viscosity. Viscosity of the liquid. So now, how do we find V here? Because this is the flow rate, which is Q. So in order to find V here, we need to use another formula. So now it's copper tube. We can find D equals to excuse me. So in this case, 32 is like this one, right? And then there's like two millimeters wall. Okay, so the overall here is like How do I draw this one? The oh, okay. The overall I mean like this. It's like from here to here, it's 32 millimeters, but the wall here is 2 millimeter. But in this case, we have both case, right? We have here 2, so it's 4, right? Both sides. This side and this side is 4. So in overall, we minus 4, we get 28 millimeter for the diameter. So now we get this diameter. It's 28 millimeter. It is equal to 0.0028. Yep. And then we can find A by this formula, pi r squared, or pi d squared over 4, which is actually like, from d over 2 overall square, so 2 square is 4. So now we have pi here, and this one is 0.028 square over 4, and the answer is 6.158 10 minus 4 m squared, which is area. Okay, so now we can find the v, which is the velocity, by q over a. Yes, q equals to av. V here, I think we should write it AV here because we have the viscosity. Sometimes viscosity is written as this cursive V. So now we have Q over A, and we get the value is 285 liter per minute. So we actually need to convert this to something else because we need this one into second. So now we can convert it as, I think we have converted in the videos in the previous one. We want this one as meter cube as well. So we can convert this one as 1 meter cube per second, which is the unit that we are aiming for, over 60,000 liter per minute. Because in 1 second, in one minute, there's 1,000 second. Oh, sorry. 1 minute is 60 second, and 1 liter is 1,000. 1 meter cubic is 1,000 liter. Yep. Okay, so that's right. And then we can get this 1 meter per as here. Okay, so now A that we found earlier is 6.1585. Pardon for my bad handwriting. Oh my god, I don't have the, the rulers, the rule page. So it takes quite a long time for me to rearrange this one. So, okay, so now let's move on to 6.158 to the 10 minus 4 meter square. So everything now we have in meter, in second and stuff. So now we can calculate the value 285 over 60,000, and everything over 6.158 10 minus 4. The answer is 7.1713 meter per second. So now we have the viscosity of this liquid is 4.11, which is in the table. So you can just, read it from the table with at this temperature, at this condition, so how much is the viscosity, how much is the n value or the density. So now we have nr, because we have found everything else now. We can find 7.713. D here is 0.028 multiplied by, there's no more multiple because we use viscosity instead. We have 4.11 multiplied by 10 to the power of minus 7, so 7.713 over 1.11, 10 to the power minus 7. The number is quite large. 59.85, or we can write it as 5.1234525 times 10 to the power of 5. So in this case, nr equals to 5.25. 10 to the power of 5 is larger than 4,000. So 4,000 is from the hint above here. So the flow is turbulent. So we can conclude that the flow is turbulent. And we can, support the evidence as nr is larger than 4,000. Okay, so now we finished 2 examples already. Let's move on to another example. Determine the range of the average velocity of flow, or which the flow could be in the critical region if oil at 60 Fahrenheit. So now they start using the US things like Fahrenheit, inches and stuff. So in this case, they gave us a steel pipe. So steel is also a good thing, steel is also a good thing. I mean, a good point to notice, because we need to see like the friction, or actually it's like the characteristic of a pipe. So you need to consider this one. You cannot just like skip, okay, 2 inches pipe, because this is only the diameter. But steel is also another important information that we have to consider as well. So now we have 60 here, we have 2 inch here. But what is the question again? The question is to determine the range of average velocity. They're not asking us to determine whether the flow is turbulent or laminar. They only ask us like the velocity. But they tell us that the critical region. So critical region is when 2000 is less than nr and less than 400. 4,000. So but it's like in between these two. So you can consider the flow as in the critical region. So we use the Reynolds number for solving for the velocity. So it is V the density over n. In this case, we can rearrange the formula, the equation, as velocity equals to nr times n here over the density. Okay, so we can find by substituting first. Okay, d here, I'll write down here, d is equals to, it's an inch, right? So 2 inch, and then Ah, we actually need to look at the table again. So let me look at the table. Um, this is quite complicated because we need to look at the table every time. Because the wall thickness is not always the same. So we have like the outside diameter, the nominal pipe size. So there are in the pipe there are outside OD, outside diameter, ID, inside diameter. So this one is outside diameter. When there's like in the example they will like show you this is the outside diameter, this is the inside diameter, and we also have like the wall thickness. So we need to consider all these things, and in this case it's 2 inch, right? So the 2 inch is nominal, why am I writing no p, nominal pipe size, and the diameter here is 2 inch. So in 2 inch we have the outside diameter as 2.375 here. We have the inside diameter as 2.067, and 2.067 we convert it to inch, we get 0.172 225, so it's 23. Yes. Yes. So there will be another table that will be very useful for you guys to see all the characteristics of each pipe. So now 2 inch here, we get the actual inside diameter. Why do we need to specify if is it inside diameter or outside diameter? Because the water or the liquid flows inside the tube. It's not like well there's like the wall thickness. Oh, in case this one is not the wall thickness. The wall thickness here is something else. It's 0.154. So as you can see that 0.154 plus 2. 2.3. Like as you know that in the pipe there's nothing usual, because when it's constructed, of course there are like the thickness depends on the steel flow of pipe or plastic pipe or something, like there's the thickness over there. So yeah, consider that, because in the exercise they told us like there's 2 inch steel pipe here, but we are not using 2 inches. We need to convert it to feet, and also we need to consider the table as well. So here is 2 feet here. For we also need to look at the table for this one. So it's 2.10 times 10 to the minus 3 pounds second per feet square, and then we have this density, which is the specific gravity, times 1.94. This is another unit for the US units. So normally we have like SG, the specific gravity, and times for the gravity, but in this case we're using the gravity of in the US units. So now SG here we have earlier, where is it, 0.89 times 1.94, it's equals to 1.7 0.26 slugs per feet. Please note that this one has no unit. So the final unit will be based on this one. So now we can move on to the next step. We have to substitute everything into the value. We have two cases. So case number one, velocity here equals to nr, because nr we can't know yet. It's like the thing that we have to determine later. So 2.10 times 10 to the minus 3 over 0.1723 times 1.26. So this is the diameter and this is the density, equals to 2.1 minus 3 over 0.1728 times 1.26. The answer is 7.061 times 10 to the minus 3, and r, because this is like the parameter that is left over here, it's not calculated yet. So in case 1, I thought my iPad is not working. So in case 1, we have nr is less than 2,000. So we have velocity here is 7.061 times 10 to the power 3 times 2,000, and it gets times 2,000, it gets 14.122. So 1228 is, we consider as 3 feet per second. And in case 2, we have the velocity is the same, because the case is based on Reynolds number only. nr, so nr here in case 2 is larger than 4,000. We can get velocity equals to 7.061 times 10 to the minus 3 times 4,000, because like in this case we can just times the number to know like whether it exceeds or stays under the number here. So 4,000 equals to, wow, that's 7.061. 4,000, here we get the number, here is 28.244 feet per second. So we can conclude that therefore if the velocity stays in the range of this one, 14.123 is less than this one, so it stays in the range between 14 and 28.244. The flow will be in critical region. The flow will be in critical region. So now we have the first one is the flow is laminar because it is less than 2,000, and this one we have flow is more than 4,000. We get turbulent flow, and in this case we get the critical region flow. So by this case we're not finding whether it is in or out, because we're determining the velocity. So the flow will be in the laminar or in the turbulent. So it's like just finding something to determine something Okay, so now let's move on to another exercise. We have determine the energy loss is glycerin at 25 degrees Celsius. So this one is another useful information, but we're not going to use inside the equation that we're finding though. So this is 30 meter, the length. So now let's highlight it. And then we have the through a standard 150 millimeter pipe. So another useful information, and with an average velocity of 4 meter per second. So in this case, why is Darcy equation here? What are you doing here? So Darcy equation here is to find the energy loss, because the question here is not finding any kind of Reynolds number or anything else anymore. We're finding the energy loss. So now let's start with the solution. First of all, in order to find the energy loss, HL is the energy loss due to friction. Okay, so before getting to the solution, I will explain this formula. HL equals to F times L over D times V squared over 2G. This is the, okay, let's start from, this is the energy loss due to friction. F here is friction factor. Friction factor. It is dimensionless. D here is, the diameter. G here is you know what it is, gravity to, alpha 9.81. V here is the average velocity. Unit is in meter per second or feet per second. This one is, it has a lot of units, n meter per n, m l lb is pounds, right? Fit per pound like this, or just fit. L, as you know, length of flow stream. Meter or feet. Length of flow stream. So now we have everything that we need to know. We find HL is equals to F. In this case, we need to look at the table of the specification of the pipe. So as from the first example here, we have already looked at the density and the end of it, so it's supposed to be the same because the type of liquid is the same. It's glycerin the same and at the same temperature as well. So density is equals to 1258 kilograms per meter cube, and this is N equals to 9.6 10 to the minus 1 Pascal per Pascal second. Not Pascal per, it's a dot, so it's like not the unit. So now we can find NR first. So NR here, still we need to find a Reynolds number. A Reynolds number is very important actually, like in all types of, wherever there are laminar flow and turbulent flow, we need to find the Reynolds number. So, and actually in flow in closed country are related to Reynolds number. Everything is related together. So now we can find the Reynolds number as V, which is 4 times Okay, so 150 will be converted into something else again. It is supposed to be 0.15, right? But it says like standard something here, so we need to look at the table again. So the table here is, it's a similar table as the previous one. We have the nominal pipe size. When they say that it's a standard one, it means that it's the nominal pipe size. So it has a different diameter from the outside wall thickness and inside diameter, which is inside diameter we have 146. Here we have ID inside diameter equals to 146 point. I will attach the table later in the description box, so you can take a look at that one, or you can actually find the lecture sheet. So 146 point, I got lost again, millimeter. So when we convert into meter, we have 4163. Okay, so this is for the diameter, and then we times 1258. So after this, we over 9.610 to the minus 1 for the answer for NR is 66.585. I'll put this one as 6 because the next number is 8. So this is the thing here. We can conclude as NR less than 2000. It's the laminar flow. So using the Darcy equation, we get F. Okay, so now we're finding the NR here because we need to find the F, which is the friction factor, is equal to 64 over this one, NR, the Reynolds number that we found earlier. So 7 here is equal to 0.03835. So we can substitute it inside the HL energy loss equation. So now we can see that the Darcy's, what is the full name again? Okay, Darcy's Weisbach equation, HL equals to F times L over D times V squared over 2G. So F now we have 0.0835 times L, which is 30 meter. Yeah, meter, so we don't have to convert it again, over D, which is 0.1463 times 4 squared over 2 times 9.81. So the final answer is 835 50 over 7 times 4 squared to 9. The answer is 13.963. Yeah, 31, so it's 3 here, meter. So in this term, it is expressed in the unit system, the SI unit system. So measuring for HL will be in M, in meter, or in other things that is in US units. So we can say so 2.963 here is equals, it's not equal, it's like equivalent to, means 13.963 Newton meter of energy is lost by each Newton of the glycerin as it flows in the pipe of 30 meter here. So this is the final answer. Now let's move on to the next exercise. I think it's kinda easy because it's only one line, but I'm not sure one line will give the easy thing or not. so now we will study something about the roughness. So friction factor here, it means like just to determine the roughness, because in this one we have like something that is inside the diameter, inside the thing inside there. So for steel we have the roughness, this one is using an inch, right? So I'm gonna give the roughness in feet, ft. Steel equals to 6.0 times 10 to the minus 3. So glass is smooth. If it's a glass pipe, it is smooth. Nothing is going to, like, if it's glass pipe, it's like smooth, flowy. I wonder like how can we use like the glass pipe in designing, so it's like perfect. So even though plastic you can see as perfect material, but plastic also have a roughness. It's 1/10 to the minus 6. It's close to, you know, close to perfect because this is very small, but still there's like some roughness there. So actually still we have, so this is called like the riveted steel, but we have another type of steel which is commercial steel, 1.5 10 to the minus 4. So it depends on the question. If the question is asking for I'm sorry if I pronounce this wrong, riveted steel here, or the commercial steel, or we have another type is like the normal steel, which is like steel, brass, copper. It's 5 times 10 to the minus 6 feet. So everything here is in feet. So now it's like the roughness is actually a very small value actually, but still we need to consider them. And we also have like the cement, the concrete type of pipe that we use for the sewer system, but now we're using the normal thing here, so don't get. So now let's look at our exercise here. Oh, where's our exercise? Determine the friction factor of water at 160. What is this? What is this called? Fahrenheit? Yeah, Fahrenheit is flowing at 30 feet per second in 1 inch. Okay, so the Reynolds number. So we're back to the Reynolds number again. Solution. Reynolds number is equals to, so tired of Reynolds number, we're gonna meet it every time. Okay, so now we have 30. So it says water. So water have another viscosity, and at a different temperature here we will have another viscosity which is different from what we have learned before. So 1 inch of this pipe has another real diameter which is not the same as the one that is inside. So 1 inch here is equals to the actual thing. Diameter is equal to 1.049 inch. And it is equals to 0.0874 feet. So now we use the feet. One feet is equals to 12 inches. 0.874 over the viscosity, which is 4.38 times 10 to the minus 5. So the answer that we get here is oh, this is a turbulent flow. It's over 4,000. 1, 2, 3, 4. Am I right? Oh, wait, I'm sorry. This is supposed to be 6. I see. Hmm? 5986 5.986 times 10 to the minus, no, not minus, power, just power. Okay, so this one is turbulent flow. Now the relative roughness, we can see that the roughness for this one, which is this symbol, is epsilon, right? Yeah, just say that this symbol is the roughness of the pipe. So in this case, we use 1.5, which is the commercial steel, 10 to the power to the minus 4 feet. So we can find the relative roughness. Relative rough. Okay, so we can write this one, turbulent. Relative roughness is equals to D over the roughness here. D, we have 0.0874 over this one, which is 1.5 times 10 to the minus 4 feet. Also, everything here is in feet, so we can just calculate it without any further conversion. 1.5 times 10 to the minus 4 minus. We get 5.82.667. Okay, so this is feet, so we can sell out this is dimensionless. So this one, it's a dimensionless ratio, both D and E, so it must be in the same unit. So in this case, if it's an inch, you need to convert it into feet first. So the Reynolds number, we look at the Moody diagram. So okay, so I will show you the Moody diagram in the next video. So I'm actually looking at the Moody diagram in another screen. Okay, so in the next video, I promise to show you the Moody diagram. It's 5.98. So NR is 5.98 times 10 to the, okay, so this is in the Moody diagram. And we can see, Moody diagram would be something like this, right? So we find this one, we project it vertically until the curve. So we have D over this one is equals to 5.583. So you see the number here. You choose it. So it's between 500 and 700. Oh, 750 if you look carefully. So you can look on your own. If you have the Moody diagram right now, you can see that it's between that. So in the vertical line, nr is equals to 5.98 times to the minus 5. So project horizontally to the left, you will see and read the value f equals to 0.023. So the question is determine the friction factor. So friction factor from the Moody diagram, from the Moody diagram is f equals to 0.02. Okay. So first of all, you project it vertically, and then you project it horizontally. So when you project vertically, you will reach, it is not reach this one. You reach, like, there's a lot of curve here, right? Curve going up and down. So you reach the curve of this one. So you can see that you project it, and then you project it vertically here, and you will read the value on the left side. So this is the answer. Yes, it is only a one line question, but that's quite long enough for us for a headache. Okay, so now we have another, if possible, one last for today. If the flow of water in the previous problem was 0.45 feet per second, so it is linked to this problem. So in this case, we have 30 feet per second. In this case, we have 45 feet per second, with all other conditions being the same. Determine the friction factor. So in this case, we need to, look at the Moody diagram again. So NR is equals to VD over viscosity. So it's equals to 0.45 feet per second. It's not a flow rate, okay? Flow rate will be in feet cube per second, like this, cubic feet per second. And then we multiply by the d, which is 0.0874, over viscosity that we have read from the table earlier, is 4.38 times 10 to the minus 6. Yeah. So 0.45 times 0.0874 over 4.3 equals to 8979.45. So this is another turbulent flow because it's, okay, 793. So dr, I mean the relative roughness, d over roughness, 0.08. We can use from the previous one actually because it's exactly the same. But we need to write it down because it's another question, right? So 5.84. So in the Moody diagram, there will be like this, like this. So you can see that the curved portion is like you drop down. Okay. You drop down here, and then you put it here. So you project it somewhere. It's around here. So let me read the Moody diagram on another screen, the imaginary screen. So now we have, okay, F equals to 0.0343 is the friction factor. The question doesn't need us to, compare, but I want to compare. So in the previous exercise, we can see that the flow rate V is equals to 30 feet per second. The friction factor here is 0.023, but this one V is equals to 45 feet per second. The F here is equals to, okay, V1, 2, 1, 2. 0.0343. So if V is large, F2 is also large. It's actually significant increase, quite a lot considering it's a friction factor because it's the third digit here, 3 and 2. So now we can move on to another example here. Welcome to another one line with this very short of the problem, and then we can see how long will the solution be. Okay, so now we can find the solution. No, not find the solution. We need to read everything first. So now we determine the friction factor F earlier as we do ethyl alcohol. So alcohol. So ethyl alcohol is 25 here. So we're not going to use this. It's just like another useful information. Flowing at this one. So we're using this one. Flowing at. It's the V. Because sometimes you can see it as flowing at some rate or flowing at some velocity. So it depends on the unit here. It's very important. In a standard steel pipe. Okay. This is getting very intense. So I forgot to include the information down here. The full name of the pipe here, I just skipped the full name of the pipe. It's called the DN40 Schedule 80 pipe. The name is longer than my name. So in this case, the diameter of this pipe, this specific pipe, is 0.0381 meter. Okay, for ethyl alcohol, we have density of 787 kilograms per cubic meter. N here equals to 1 times 10 to the minus 3 Pascal second. And also for NR, Reynolds number is equals to VD over this one. So now we have 5.3 meter per second times 0.0381 meter times 787 here over 1. Oh, I don't need 1 here. It's 10 to the minus 3. So now 0.0381 times 787 over 10. The number is too large. 15891.91 equals to 1.589 times 10 to the minus 10 to the power of 5. So it's turbulent. So right now you don't need to write it's over or shorter. I mean less than or over, because as you can see, if there's over 4,000, it's turbulent so automatically. So now for the steel pipe, this one, because it says like the standard steel pipe here and with this specific name, so if you can see in the table, you can get the epsilon equals to, I'm sorry if I call these symbols wrong, but I think it's epsilon, 5 meter. So now we can find the relative roughness equals to 0.0381 over 4.6 times 10 to the minus 5 equals to 0.0381 over 4.6 times 10 to the power of minus 5 equals to 828.2608. Okay. So now we can read the value of friction factor is it's in the graph, so I'm reading is another screen. You can imagine, or you can read at the same time with me. Um, okay, I found it. So it's F equals to 0.0225 with the variation of 0.00. Oh, how many zeros is 3 zeros 5? Oh, this is dimensionless? Yeah, dimensionless, so you need to consider about the units. Okay, so this is all for today's video. I have another 9, wait, is it 9? Oh, 10 exercise coming. I don't guess we can finish in 1 hour, so I'll finish for this video for now. You can see it roughly. Yeah, so it's quite longer and more complicated than this exercise here. Yeah, it's longer exercise. It's not like the you know what we say, that just the small one, not the small one. What is that called? The simple one and the complicated one, right? Okay, so now let me go over everything again. In the next video, I will show you the Moody diagram, so stay tuned. It's an episode, so stay tuned for how to read the Moody diagram with ploy. Okay, so now we have what we have done so far. We have completed 7 exercises in 1 hour, so I hope in the exam we can do it as well. Yeah, but it's only one topic, so it's like going from laminar to turbulent, turbulent to laminar, so it's kind of like we can predict what formula we're going to use. So now let me summarize it again. If it's going to be laminar like this, and Reynolds must be less than 2,000, and if it's over 4,000, it means that the flow is turbulent. So if it sits in between 2,000 and 4,000, it means that the flow is critical region. So now we have this one formula for the Reynolds number, and then we have another formula for the Reynolds number, which is we use viscosity instead of density rho over n eta, I guess. Yeah, the symbol name is eta, right? And then we have to find, so in this case we only find the Reynolds number to determine the flow, the type of flow. But in this case we have to determine the range of velocity. So now we have to find the range. Oh, sorry. We have to find the range. This one. So now we have the range here that makes the flow in the critical region. So now we start using the Darcy equation. I think it's everyone's favorite to use the Darcy equation since we have done the assignment earlier. So now we have HLF. So HL is energy loss due to friction, L is friction factor, D is diameter, this is gravity. Oh, don't forget gravity in this is in SI unit, but in US unit, another one, I think 1.94. Yeah. So now we have everything here. Okay. The next problem here is to find the friction factor, which we're going to use the Moody diagram. And the next one we change the velocity, and then we can use the Moody diagram again. And the last one, we're finding the friction factor, but we have a different liquid here, and this is the standard name that I forgot to include, so don't forget to write it down on your sheet. I will upload a sheet in the description box below. And we will use, well, this Reynolds number, it depends on the given information. So if the given information is like we can use the viscosity, then use the viscosity. If you don't have, we can use, so we use this one. It depends on the problem. And this one, there's another table. So you can actually see the table inside the sheet. There's like the table for roughness, the table for OD and ID, outside diameter and inside diameter. So as I mentioned earlier, if the diameter is like this, we need to time the inside diameter, the wall time 2, and then the overall diameter minus the 2 wall here. So we get the inside diameter that we want in this case. But in another case, they give us like standard wall, standard diameter. So all we need to do is to look at the table, and this diameter will be something else that is not equivalent to the problem one. So that's all for today. Stay tuned for the next video that will include more complicated complicated problems and the Moody diagram. So thank you. Bye bye.